Okay, we're on. Good morning, everyone. Welcome back for another week. Uh, yeah, it looks like we lost a few. Maybe they'll probably show up. Okay. Um, so where we are is we're still in the middle of discussing things from linear systems, and especially today we're going to talk about Fourier analysis. We probably won't get to the probability and statistics material today. Um, Assignment 1 due Friday. We should, I think, finish the material you would need for assignment 1 today. And that's pretty much where we are. So we're going to kind of pick up with Fourier transforms. Before I get started, anybody have any questions at this point? Okay. Good. Okay. Well, thanks. I got to talk to everybody one-on-one last week. That was great. Enjoyed that. Office hour. Sorry, haven't determined it specifically yet, but based on the poll that I saw, looks like Friday afternoon. I'll get you the exact time after class. And again, we can schedule another time if that doesn't work for you. Okay, so we're going to pick up where we left off, which was here. We had just kind of barely said the name of the Fourier transform. That's about as far as we got. Okay. And there are different forms of Fourier transform, and we'll actually talk more about the relationships between these things later. Again, for now, it's not going to really matter. You see Fourier series and you see Fourier transform, and of course they're very closely related, really. Just people use them in maybe slightly different ways. And the discrete and continuous versions are related to each other as well. But for the most part, the ones that we're really going to be dealing with are going to be, well, this one, right? And so when we deal with continuous signals and continuous systems, we kind of model them as going on forever. So they're continuous, they're infinitely long from time of minus infinity to infinity. And as a result, that's kind of a theoretical thing, because we don't really use it that way in practice. The way we use it in practice on a computer like MATLAB means we have to have things of limited scope, right? We have to have non-infinite data, and we have to be able to compute at discrete points. And it turns out that even though we call it Fourier transform, it's probably what we do in the discrete world is probably more closely related to discrete Fourier series. But we'll explain why that is later. Okay. So with that introduction, okay, so the equation for the continuous Fourier transform and its inverse looks like this. Okay. And in this case, we have it kind of set up for radian frequency, right? And so radians per unit time, usually per second, but doesn't have to be. It depends on what the units of our time t are, is the way we will look at that. But the other thing to recognize is that omega is equal to 2 pi. Unfortunate use of f here, but I'm going to use f anyway because that's how we're mostly going to use it. And so if this is radians per second, then the units of this are going to be cycles per second. And if that's cycles per second, that's also hertz. And I want to emphasize, and I will emphasize this again, that's the only thing that hertz is, cycles per second. Okay, so if it's radians per second, the units are radians per second, not hertz. If it's cycles per hour, the units are cycles per hour, not hertz. Hertz is only cycles per second. Okay, and the reason for this conversion, hopefully this is not too hard to remember, is that there are 2 pi radians in one cycle, right? 2 pi is what it takes to go all the way around a circle. So hopefully that's not too hard to remember. Okay, and so all the units work out. All right, so we alternately use radians per second, cycles per second, and you'll find that I am, well, I am a stickler for units because it's really important. Because one of the important skills to come out of this class is for you to be able to analyze data in the frequency space and relate it to what it means in the real world. And if you're going to do that, you need to be able to use real world units. Okay. So that's where we're headed. Okay, and so that's the continuous case, right? The discrete case, which some of you will have seen and some of you maybe have not seen. Okay, it's a little different. It's basically the same equation. Okay, if we have an infinitely long sequence, and this probably should go from negative infinity to infinity, but it's not going to matter for what we're doing. Basically, you have your function and you have the complex exponential there, right? Which again was the complex sinusoid, which has a real part and then an imaginary part that's 90 degrees out of phase with it. And so that's similar, right? And we get something in the frequency domain. Let's see, yes. But again, what we end up really doing for a finite sequence, because again, in MATLAB, we can't compute this for something infinitely long. It has to be truncated at some point to a certain number of time samples. I'll try to be careful about using that term. And so this basically says that the length of the sequence is capital N. Okay. And we would refer to those as time samples. And more about this later, but hopefully that's not, too hard to deal with. Basically, we're talking about a vector of length n is how we would represent it in MATLAB. N data points in sequence. And then you see it has the similar form, but then it has this thing that looks a little more complicated up in here. And of course, we're using f now, small f, as our frequency variable. We'll talk about the units of that in a second. But basically, we have a complex exponential. It is these are discrete now sinusoids. We'll look at what those look like in a bit. But it's a little bit more complicated up in here. The inverse transform is similar. Basically, you're just taking the complex conjugate of that complex exponential here and applying it to the frequency domain data in order to invert it. Scaling factor, just again, to keep things honest, so that when you transform and transform back, you get back what you started. Okay. Okay, so this is what we end up using when we do Fourier transforms in MATLAB. Okay. And again, I'm not going to ask you to actually apply that equation because MATLAB does it for you. Okay. Just again, understanding basically what we're doing here. Now, we're taking our function in the time domain, right? And you could say what we're doing is decomposing it into a sum of these complex exponentials, which is basically what we're doing. We're taking a dot product of our function with every one of those complex exponentials. And then the result of that dot product is what goes into that particular frequency space. Now, earlier we had an omega up in here, right, for the complex exponential, but now it's written with a 2 pi over n times f. And the question is units, okay, because now the units are going to be different than what we had in the continuous case. Remember, continuous case was either radians per unit time or cycles per unit time. Okay, this is going to be a little bit different when we take Fourier transforms in MATLAB. And if we do kind of if we think about kind of a dimensional view of this thing, so this stuff here in the box must be unitless, or a scalar if you like, because it is the argument of an exponential. Okay, so hopefully you can accept that assertion. And so, excuse me. So if that's going to be unitless, then all of the units of these things end up having to cancel out. And so if we say, okay, what do we have there? I have a 2 pi. Well, as we said before, 2 pi is radians per cycle. We use those terms for that. We have n samples, or time samples, if you like. And I'm going to put here to kind of balance that one recording period. In other words, that's how long we recorded the signal for n samples. Okay, we're not, we could consider that in units of time, but a time sample is a unit of time. Okay, so we'll go with that. And then we have f, and I'm going to leave that one open for a moment because that's the thing we're trying to actually find the units of. Or no, I'm sorry. Yes. Okay. And then k. Okay, sorry, I've made a mistake. It's not unitless. Radians, which is sometimes considered unitless, because remember, this is a cosine of something plus j sine of something. And so the arguments of the cosine and sine should be in radian format. So I apologize for that. Okay, and then we have k, and k is just samples, right? Those are the units in which we mark our time signal. Okay, now if I want all that to cancel out and become radians, oh good, I can do this today. I can use colors. Then, okay, well, samples cancels out with this samples. I want to be left with radians. So F, when written in this form, is cycles per recording period. In other words, that's the number of cycles per total length of the signal. Okay, so at the moment, I'm hoping you will, take my word for that. Okay, but we'll see why that works out in a little bit. And by the way, f takes on values of 0, 1, 2, 3, etc. In other words, integer values. Okay. All right. Does anybody have any questions about that? So when we're doing this, just to summarize, when we're doing discrete Fourier transform, in other words, doing Fourier transforms in MATLAB, the frequency units that we get are going to be in terms of cycles per recording period. Now, if you know this recording period in real time in seconds, you can convert that to cycles per second or hertz. But the numbers that we get are not going to be directly in hertz. Okay, we'll see an example of that in a bit. Any questions? Okay, all right.
Could you please explain about what was K again?
Oh, K is just the units of time, but they're discrete units of time, right? So, you know, there'll be an X of 0 and an X of 1 and an X of 2. But since this is a discrete signal, we don't know what happens in between those. So we would basically see it as something like this, and so on, where 2 comes after 1, 3, etc. K. It would look like that, right? And the only thing we know about it is these, because these are the kind of signals that we actually work with in MATLAB. Does that make sense?
So the unit is like samples because it's the number of samples we have.
Yeah. So this process of taking, you know, measuring the signal at discrete times, we refer to as sampling.
Oh yeah.
Okay, and so each of these are time samples. Okay. Now when we go to measure this signal and sample it at different times, there is some real time, you know, we set that up in the measurement system. We said, okay, this is the sampling rate, or this is the sampling interval, you know, how many seconds or milliseconds or microseconds between each one of those. So a sample is a unit of time, really, but it's dependent on how we did the measurement. Okay.
Thank you.
All right. And we will find that there's a lot of things you can do in kind of discrete Fourier analysis that are independent of the actual real world time that is. In other words, we can work in units of time samples and apply the same thing to different cases that might have, you know, different real world sampling intervals. So it's, you know, one of the, I guess, things to be able to do is to be able to work in both of those worlds. Okay, any other questions? Okay, all right. This is just going back to the continuous case, and the thing that the whole point of this slide is to point out that this is complex. Okay, it has a real part and an imaginary part. Okay. And by the way, just again, hopefully to remind you of this, the equivalent of a number line for imaginary numbers is a number plane. Okay. And so we can take any complex number with its real and imaginary parts, and it basically represents some point in this real imaginary plane. Okay. Hopefully that's familiar. And then we also have an alternate representation. Okay, I missed, but you get the idea. In terms of magnitude phase format. So since this is a point in a plane, essentially, we can represent that point in the plane by its by essentially its real imaginary coordinates, or we can give it a polar coordinate representation by its magnitude and an angle, which we will generally refer to as the phase angle. Okay. All right. So, we can look at things either way. In general, for our purposes, the magnitude phase representation is going to generally be more useful. Okay, so this is a complex valued function on frequency. Now we'll come to some of the practical things on that in a second, but the primary reason why we spend time with the Fourier transform is this. If we have a linear shift in, so remember we talked about our linear shift invariant system, maybe it's a black box, but we represent it by its impulse response in the time domain, h of t. Okay, so again, when I say impulse response, there we go. I specifically mean that. And by definition, that's what we get out of the system if we put a delta function into the system. Okay. So we can represent this by h of t, but an alternate representation of it, a model, we'll say, is what's in this dashed line black box, which is to take f of t, take its Fourier transform, that's what that funny scripty f thing is, multiply by h of omega, and then that's inverting the Fourier transform. Okay. Now, when you build a circuit with resistors, capacitors, inductors, and it's a linear system, it obviously does not do this. In other words, it does not compute a Fourier transform, multiply, and invert the Fourier transform. But this is a mathematical model that applies to linear systems. Okay. So if you know h of t, the impulse response of your system, then you can either do convolution with f of t, right? F of t star h of t would give you g of t, or you can compute a Fourier transform, multiply by the Fourier transform of this, so h of t and h of omega. Hopefully that's clear. Those are Fourier transform pairs. And then invert the Fourier transform, and you should get the same result, right? Those are equivalent ways of doing things, and that's the convolution property of the Fourier transform. On the other hand, I can write a computer program that does this, and it's a linear shift invariant system also. Okay, and I could get the equivalent result from that computer program that does Fourier transform, multiply, inverse Fourier transform by inverting the Fourier transform of h of omega, getting an h of t, and doing a convolution. Okay. In most cases, depends. In most cases, this is, well, depends on the length of h of t. If h of t is long, then it's more computationally efficient to do a Fourier transform. If h of t is short, it's more computationally efficient just to do a straight up convolution. Okay, so it depends on as far as that goes, but again, should be equivalent with the, within numerical precision. Any questions on that? That should be familiar. Okay. All right. So there's, significance associated with this guy, right? Also, because we said for a linear shift invariant system, if we know this, we know everything we need to know in order to calculate the output for any input. Okay. Well, since these are the same information just presented a different way, really, that's what the Fourier transform is doing. If we know this, capital H of omega, we know everything we need to know about the system also. Okay. Because if we know that, we know this, and vice versa. Okay. So, they're just two sides of a coin, really. They give us the same information in different ways. So the significance of capital H of omega, we call that the frequency response. Okay, probably heard that. For a linear shift invariant system is the Fourier transform of its impulse response. Okay, now remember though, this is complex. In other words, it has magnitude and phase components, or real and imaginary components. And so the kind of symbology we will use for this is the magnitude of that result. We'll use absolute value or magnitude indicators on it. And the phase response, which we don't, I'll say, often don't pay a lot of attention to, but there are reasons to do that, which we will explain later. Generally, I'm going to write this way. It's still a function of omega. Okay, it's a phase angle, and I'll use the subscript h to indicate that. But we won't be writing that very much. Okay, most of the time we'll be looking at magnitude responses, but not always. Okay, so basically it's to say, okay, we take the Fourier transform of the impulse response, we get a complex function, I guess you could say, on omega. And if we take the magnitude of that, of all of the elements of the Fourier transform, that's what we got here. Okay. Magnitude response. Sometimes we will also use, we will square that, because that has to do with, that puts it in units of power. But that's obvious what that means, so that's okay. Okay. And I will also, well, actually, let me point out something about this right now, because we'll come back to this later. We can also talk about the real part of h of omega and the imaginary part of h of omega. Again, just as we said before, with any complex number, we can do that. And so just to be clear, the magnitude squared is equal to the real part squared plus the imaginary part squared, right? Again, that's, if you look at it in that complex plane, the real and imaginary axes, that's just Pythagorean theorem, okay? But, okay, we can also, and it's usually going to be a little bit easier, that the magnitude squared of a complex number is actually equal to the complex number times its complex conjugate And so we will refer to complex conjugate from time to time. And in order to form the complex conjugate, can anyone tell me a simple way to do that?
Isn't it just you take the imaginary part and make it the opposite sign?
Right. So basically negate all J's or I's if you're using I. Okay. But all of them, not just one or two. Okay. And that basically negates the imaginary part of that number. Okay. And I bring that up because I will use this in some examples, and it's generally the easier way to find a magnitude squared than doing this. Probably some exceptions to that, but usually. Okay. Any questions on that? And these are, again, these are things that, yeah, you've probably seen them before. They're going to come up again, and I'm just kind of introducing the language right now. Okay. So what does this mean, right? We have a magnitude response and a phase response associated with a system. Well, the magnitude response changes the amplitude of a sinusoidal input of a particular frequency. So remember that the whole point of, or I won't say that, but maybe the way to think about the Fourier transform is that we're taking a time domain signal and just breaking it down into a weighted sum of sinusoids, right? And so, if I have x of t, I can kind of think of the Fourier transform as decomposing that into, an element of this frequency and an element of that frequency. And stop doing that. An element of another frequency, right? And so basically x of t becomes a weighted sum of all of these frequencies. Well, when we put x of t through a linear shift invariant system, this system is going to scale every one of those frequencies. It could amplify them, it could suppress them, it could leave them the same, right? And so basically the magnitude response tells us how much the amplitude of any particular frequency is changed by that system. Okay. The other thing we can do with the sinusoid is we can shift it in time, right? We can cause a phase change to happen, and you can think of that as a time delay or something like that, because if you take a sinusoid and you back to red and you delay it in time or phase shift it, something like that. Basically, if you phase shift it, it's like causing a time shift of it. Okay. And so this is the other thing that a linear shift invariant system does to different frequencies, is it phase shifts them or equivalently time shifts them. But this is a function of frequency. And so what we may find is that some frequencies are not changed and other frequencies are time shifted more, which has some implications we'll talk about later. Okay. So these two things together are essentially what linear shift invariant systems are doing to our input signal. And so if we think about basically say, okay, our input signal, a model for what's going on is our input signal goes into our linear shift invariant system, and we can model that as saying, okay, we break it into all of its different frequency components. Each of those frequency components is affected in a different way by the linear shift invariant system, either by affecting its amplitude and or affecting its phase. and then we put them back all back together at the end. And that's what we get out. Okay. That's more or less what this process is talking about. Okay. So, and again, because we're multiplying here by a complex number, we're affecting both the phase and amplitude. Okay, any questions about that? Okay, so this is the this is one of the significant ways of looking at things that the Fourier transform enables us to do. Now, it only applies to linear shift invariant systems. I'll keep bringing that up. Okay. If it's not a linear shift invariant system, then we can't model it this way anymore. Okay, one other thing about Fourier transform right now is what I call a frequency time relationship. And basically that if something is large or lengthy in time, then its Fourier transform is going to be small or compressed or short in the frequency domain, and vice versa. Okay. Now, the kind of intuitive way to look at that is to say, okay, if something is is a short feature in time or a small feature in time, is basically going to mean I'm going to need some sinusoids that are of relatively high frequency in order to construct that. Okay, whereas something that takes longer in time, is bigger, maybe doesn't need so much high frequency content, because high frequencies are going to give us sharp transitions and things that happen quickly, right? And so when we think about, how do I construct this out of sinusoids, or how do I construct that out of a bunch of sinusoids? Well, it's, they're going to have different content at different frequencies. And so the blue, its Fourier transform looks like that and has a lot more content at the higher frequencies than the green, which has a lot more, which has the bulk of its content at lower frequencies. By the way, when we take Fourier transforms in MATLAB, and we'll explain why this is later, the highest frequency is the halfway point. Hopefully you've seen that, maybe not. Because, and again, more explanation later, in a discrete system, there is a highest frequency you can represent. There's a limit to the highest frequency. Okay. In a continuous system, frequencies can go all the way out to infinity. But when we're working with discrete systems in MATLAB, basically there's a limit. Okay, it's the Nyquist limit. For those of you who know about sampling, we will explain that later. But for now, you're going to have to take my word for it that the halfway point, in this case 256, is the last unique value. Everything above that is a mirror image of what happens here. And so these are not actually higher frequencies. The other interpretation for this stuff is this is the negative side of the Fourier transform. Because of the algorithm used to compute the Fourier transform, it appears in the top half here. Any questions about that? I'll remind you of that.
I have a quick question, but it kind of relates to the homework. So
Yeah.
if this is not the time, okay.
Go ahead.
When I did the final part of like the MATLAB portion of the homework, and I took the Fourier transform, I remembered this relationship with that it should be inversely related. But when I took the Fourier transforms, the shapes actually corresponded a little more directly, which was strange. I thought like the one with the largest width in the time domain, its Fourier transform also had the largest width, which I thought was strange. How could I explain that?
So one thing to be careful of there is that you have them scaled properly, in order that the levels are comparable at frequency 0, or the first element.
Can you repeat that?
Yeah, so I think I mentioned this in the assignment, that normalizing them so that the area under the curve is in the time domain is equal is important, because then when you take the Fourier transform, they will all come to, let's say, they all come to 1 at 0 frequency.
Yes, I did that.
Okay.
Hey Noah, I also did that last portion, but I got sort of what was expected, where the wider width had more like of its frequency domain more towards the lower frequency. So
Okay, well, maybe Noah, we can discuss that offline.
Yeah, that sounds like a good idea. Thank you.
Okay. All right. But yes, that last part of the assignment is actually meant to demonstrate this. So that's the result you should get. Okay. All right, so remember halfway, so a lot of times I will only display this up to the halfway point. Okay, because the second half is redundant. This is just zooming in on the lower end, and of course, again, you can see now I haven't these. Oh, actually, wait a minute. No, these don't have. Well, they might have the same area under curve. Actually, I think they do. If basically so 0 frequency is going to be proportional to the area under the curve, or actually equal to the area under the curve in this case in MATLAB. And so a lot of times we normalize things in order to be able to compare them, so that you get everything has a value of 1 here. Okay. Okay, and so you can basically see that this being narrower basically has much more content at the high frequency. They all have these are, the rectangles are probably bad examples because they have to have high frequency content, some at the edges here, in order to form these kind of straight sudden increases. But the basic idea is there. So, okay. And then as a practical note, in MATLAB, we're using a function called FFT, which is the fast Fourier transform. And the fast Fourier transform is just an algorithm for quickly or efficiently computing the discrete Fourier transform. That's all it is. Okay. I had to learn what it was. You don't have to, because so many programs have been written with that algorithm that it doesn't matter. It just takes advantage of recursion and things in order to compute the Fourier transform efficiently, and was, I'll say, well, it's still important, but was more important in older days when computers weren't quite so powerful, right? So the efficiency maybe is less important, but that's not totally true, because now you can do more demanding things, but you still need the FFT to do them efficiently. And so again, you're going to get the mirror image kind of thing. And so you can think of, this upper half as belonging here at the negative frequencies. And you can also think of it as being redundant with everything that's here. And so there's nothing unique up in those parts. So, and the caution there is, don't let that confuse you that, oh, there's high frequency content way up here in this thing. This is not high frequency, okay? This is just the mirror image of this stuff right here. And so it technically is actually low frequency content. Okay, the highest frequency in this case is 256. If this was 1,024 long, the highest frequency would be 512. Okay. Another note about the FFT, it's most efficient when the data length is powers of 2. That's why you see we often use data lengths of powers of 2, 512, 1024, etc. But it doesn't have to be that way. It's just you can compute an FFT for a data length of 1,000. It's just technically not quite as efficient as doing powers of 2. Okay. That's the end of that set of slides, which is going to lead us into the next set of slides. But good time for a stretch, I think. I don't have my 2-minute timer up, so I will shout when 2 minutes are up. Okay.
Hey, Dr. Lelouch, I had a quick
Yeah.
question. It's not really related, but you said
Sure.
for powers of 2, is that just because of the recursion stuff
Yeah.
that you're talking about before?
Yeah, that's exactly it. It's the way that the recursion works on kind of different layers. It just goes by powers of 2.
Okay.
I honestly have never looked at the algorithms for non-powers of 2. I had to learn the power of 2 approach to that. I never actually went to see how they do it for non-powers of 2. So, and there are other transforms that work that way. There are wavelet transforms that work that way too.
Okay.
And the same applies to images, actually. Multi-dimensional Fourier transform. You'll see we often use powers of 2, but not always, for the size of the images and things.
Okay, thanks.
Okay. So we're going to carry on with Fourier transform properties. So I asked you to take a look at this worksheet because some of these properties are going to come up. Several of them already have, actually. And so I think it's useful to kind of review some of these. Hopefully this is going to work. Okay, so I want to go through these kind of quickly. Most of them are pretty familiar, and we've actually already addressed them. So, for example, what they call superposition principle just derives from the fact that the Fourier transform is a linear transform or linear system, and so basically says, "Is this going to work? Tell me you're going to work." Basically, the Fourier transform of a sum is the sum of their Fourier transform. Oops, that's a cue. Where's my eraser? Right. The shifting property is one we will make use of. Did anybody obtain that?
Yeah, is it just e to the negative jwa times the p of w?
Yes. Okay, so basically shifting the function in time is only going to affect the phase. So this is a phase term here. It doesn't change the magnitude. Okay. So that's the, the practical significance of that. In other words, you need all the same frequencies in the same proportions to construct that function, whether you move it over in time or not. It's simply that they're going to have different, they're going to all be delayed by a different amount of time. It sort of makes sense, I hope. How about scaling?
Yeah, isn't it like P of omega divided by A, and then all of that divided by the magnitude of A?
Yeah,
What I have.
it's something like that. The important, yeah. So there's a scaling factor and so forth. But you'll find I tend to not pay a great deal of attention to scaling factors. Okay. The important thing is this. In other words, right? If we expand something in the time domain, we're going to shrink it in the frequency domain, which is just that property we just talked about, right? If we take a function and widen it in time, we're going to have the same Fourier transform. It's just going to shrink in frequency, and vice versa. Okay, we're going to refer to that a lot, and maybe again, we aren't going to be computing Fourier intervals and things like that in this class, so just be aware. Okay, the symmetry properties are important and again, there was nothing to really fill in here, just to kind of recognize that they exist, is that a function that is all real and has even symmetry, and what we mean by that, of course, is that is symmetric with respect to 0. So a function like that is going to have a Fourier transform that is also all real and has even symmetry. Okay. Now, the thing is that actually real begets even. Okay, so it's not. It would be easy to think that real gives you real in the transform domain. That's not true. Okay, if you have an all real signal in the time domain and you take its Fourier transform, it will be symmetric in the frequency domain. Which, by the way, is what happened here. So all the signals we're going to deal with are all real valued in the time domain. Okay. And so when we take their Fourier transforms, they're going to have symmetry. You remember, this is the negative part, and therefore this is the same as that. It has to be symmetric. Okay. You might say, well, when would you have a signal that is not real valued? Well, an example of that is actually in MRI, we or they will construct a quote imaginary signal because you can take two measurements that are 90 degrees out of phase with each other, just like the sine and cosine of our complex exponentials are 90 degrees out of phase with each other, and you're taking advantage of that complex in constructing a complex valued signal. But you've constructed it. We can't measure imaginary signals because they're imaginary. You can imagine them, I suppose. Anyway, so there are, from a mathematical standpoint, there are actually ways to use that in a meaningful way in certain applications like MRI. Okay, but for our purposes, all the signals that we measure will have real symmetry in the or will be real valued in the time domain, which means that all of our Fourier transforms should have symmetry. Similarly, if we have, although this isn't going to happen very much, right? If we have even symmetry in the time domain, that's going to give us an all real Fourier transform. Okay, but a lot of our signals are going to be measured from time 0 because that's got to be symmetric with respect to time 0. Okay, so, you know, from a this is a less practically applicable than this is, okay, but it is true. Okay. Any questions on that? Okay. Well, convolution we have already discussed, right? If we convolve in the time domain, then we multiply in the frequency domain. But again, those may be complex numbers we're multiplying, right? Parseval's theorem, again, is just stated here, but you know, there's a couple of different practical ways of looking at that, but more or less, Parseval's theorem just says that it's a complete transform, that there's no information lost. And this is done in terms of power or energy. It says the total energy of the thing in the time domain is equal to the total energy in the frequency domain. But another way of, you know, looking at that is that basically no information loss. In other words, we can transform something and then transform back and we get what we started with. There's nothing lost in the process. And, you know, there's a number of different ways of kind of saying this, but the fact that there's no information loss means that those are perfect alternate representations of that signal, right? We measure it in the time domain, we can take it to the frequency domain, and this, you know, the same information is there, it's just arranged in a different way. Okay. So that's, you know, kind of the practical implication of Parseval's theorem. Not all transforms necessarily would have this. Fourier transform does. Transform of delta function, well, that was on the pretest, and most people know that that is equal to 1. How about the transform of a Gaussian? That one's a little harder to find. No, well, the transform of a Gaussian is just another Gaussian, which is why I use it as an example all the time. When it's written in this form, it will be e to the minus 1/2 sigma squared omega squared. Okay, so a Gaussian function gives you another Gaussian function. Now the Gaussian function is the bell curve. You'll find that when I just like draw examples, I very often do Gaussians, as I did earlier on this page. And of course, the last problem on the first homework is working with Gaussians, okay? And so you should be familiar with the Gaussian function because I use it a lot. It is anything of the form e to the minus x squared, or e to the minus something squared. That's a Gaussian function, okay? And then, you know, you probably saw this in probability and statistics because this is the functional form of the normal distribution. Again, what was often called the bell curve, okay? And sigma is a parameter that determines how wide that is. Okay, so the larger is, and again, in statistical context, that's the standard deviation, right? But in a statistical context, that's what that means. But if it's just a function, there is a sigma parameter that basically determines the width of that function. So you'll notice we have the sigma, it appears in the transform domain, appears in basically inverted form. And so the width of the Gaussian in the Fourier space is basically inversely related to the width of the Fourier transform, width of the Gaussian in the time domain. In other words, if this is a wider Gaussian in the time domain, that gives us a narrower Gaussian in the frequency domain. Okay, again, that's one of the reasons I like the Gaussian, because it demonstrates that principle pretty readily. Okay, any questions on that? That should be well, it definitely will be a familiar function by the time we're done here. Okay, because it's got a lot of purposes. It's used a lot in image processing. It's very useful function. Okay, any questions on any of those properties? That, again, we're going to refer to them quite a bit. For our purposes, we're not going to do Fourier integrals. I'm not going to ask you, okay, what's the Fourier transform of this thing? If you have to take a Fourier transform, it will be something you can look up in a table, but you may have to manipulate a bit with properties also. Okay. Okay. Now, so we've done that. The Fourier transforms you should know. So first of all, so these are ones, again, you'll be able to look up anything in a table, but kind of qualitatively, you should know these functions, okay? The delta function, well, we've talked about that a lot, right? Its Fourier transform is a constant. And by the way, all of these are vice versa, right? So the Fourier transform of a constant is a delta function. Okay. The rectangular function its Fourier transform should be familiar. Oops. As the sinc function. And no, I can never remember the exact relationship, so you always have to look it up. Okay. But Fourier transform should give you a sinc function. And remember, this is this would be like sine omega over omega. Okay. So you should know that rectangular function, sinc function are Fourier transform pairs. And then you can imagine, based on what we've said, that the wider the rectangle becomes, what's going to happen? The narrower the sinc function becomes, right? So again, using that property, we can use that in a lot of different ways. Okay. The cosine function who remembers its Fourier transform? Nobody?
It's just like one frequency, right?
Just one frequency, right? It's a delta function at omega naught, the way I've written this, but then we need a balancing delta function over there. Okay, and so this is an example of symmetry, right? The cosine function is symmetric with respect to 0. So it has a symmetric pair of delta functions. Okay. And another way of looking at that, right, is that cosine of negative omega 0, omega naught t is cosine of omega naught t, right? The cosine of a negative is just the same. And so those positively reinforced for the real part, but the imaginary parts of those two cancel out to give us the cosine. In other words, there's no j sines left because each of those guys cancels them out. Similarly, the sine, right? If let's see. Of course, the sine function, you know, is shifted. Okay, so the sine function being shifted basically is going to give us, you know, one here, but an inverted one here, so that the cosine parts cancel out, but then the sine parts kind of stick around, and they're scaled by j, as I recall. Okay. Anyway, usually we'll just deal with cosine in that case. And then finally, as we just talked about, the Gaussian function, right? You should know that guy is a Gaussian, but the sigma parameter that determines the width is inverted. Okay, so if this has width that goes as sigma, then this one has a width that goes as 1 over sigma. Okay, those are the ones we use as examples all the time. So those are ones I expect you to kind of recognize. And again, the functional, you should be able to recognize the functional form of the Gaussian in general. If you see something that's e to the power negative power something squared, that's a Gaussian in some form or another. Okay, and you might have to manipulate it a bit to get it in the same form as the transform table, but you should recognize that. Any questions on those functions? Okay. All right. I think we have time for a little, we're going to have to continue on a bit more with Fourier next time, but that's okay. We can take a quick look at this example problem. Okay, so so basically we have a system with an impulse response given by this. This is a discrete system. So basically 0.6, 0.3, 0.1, then it's done. Okay. First question, what's the step response of this system? So a unit step is going to be basically dot, dot, dot. So the question when we ask step response, what if we put this in? Basically, it's a value 0 up to time 0, and then it goes to a value of 1 and stays there forever. Okay, this is k. If we put that into the system, what kind of output do we get? Well, so we could sit down and do convolution, but we're not going to. Okay, so what I want you to recognize is that every one of these is a delta function, and every delta function is going to give us one of these. Okay. So when we think about, let's see, we'll start. When we think about that, so if we first think about this guy, well, he's going to give us a 0.6, 0.3, 0.1, right? 0.6, 0.3, 0.1. Okay. And then we think about the next one. We'll color him green. Well, he's going to give me the same thing, but delayed in time by 1 unit. So 0.6, 0.3, 0.1. And then finally, we'll use one more. I'll use purple. So that one is also going to give me 0.6, 0.3, 0.1, and so on, right? And so the result of all that, and again, the system is linear, so we add those responses all together this way. And so we're going to end up with, well, the only thing we have in the first position is 0.6 from this guy. That adds up to 0.9. And then the 3 of these are going to add up to a 1.0. And hopefully you can see that everything after that is going to have a 0.1, 0.3, and 0.6. And so it's going to stabilize as 1.0 forever. So we just did convolution, actually, but not in any, probably not in any way you learned to do it. Okay, and the importance of doing it this way, and again, this works for discrete cases, is because it illustrates what's really going on, right? Every element of the input generates that as output, and then they all get added together. Now, notice that because this is shift invariant, this thing never changes, right? So they all, in this case, they all generate the same one, same wave shape. And because it's linear, we can add them all together. So again, this only applies to linear shift invariant systems, but it works. Notice also that, so what happens with this system? Well, as it basically can't, the output can't respond as quickly as the input does. In other words, the input comes up really fast, but the output can't come up quite so fast and takes a little while to settle out. That makes it a low pass filter, as we'll see. Okay. Okay. We're out of time. So I think we're going to stop there and just carry on with the rest of this example next time, which means that, yeah, there's a case like this on the homework. So, we'll need to do a little bit more with that because I'm out of time. Anybody have any last questions? Okay, if not, going once, going twice, going 3 times. Okay. I will, stick around.